Hello Math 111, I'm McKenna and we will be discussing 13.6 and 13.7 sections on cake division procedures regarding proportion and the problem of envy. We will be discussing how dividing something equally between a given number of people can be more challenging than it seems. We'll go over a brief history of the cake division procedures and the two proportional procedures established by Hugo Steinhaus, Stefan Banach, and Bronislaw Kastor. By discussing the difference between the long divider and the last diminisher method, differentiated by these mathematicians, we can establish how it relates to the bigger picture of the common sharing methods of today.
The modern era of fair division began in Poland during World War II with a man by the name of Hugo Steinhaus. Hugo Steinhaus was born in Poland in January of 1887. Steinhaus would later in his life spend 5 years studying mathematics at the University of Göttingen. Shortly after graduating, he proposed and would help lead the creation of the Polish Mathematical Society during the 1920s. To get to Steinhaus's contributions to fair division, we actually have to go all the way to the 1940s. In 1944, Steinhaus proposed the problem of dividing cake into pieces that were both proportional, where each person was satisfied with their share, and envy-free, where each person was satisfied that nobody was receiving more than a fair share. His work brought him to the cake division and lone divider procedures. While Steinhaus's procedures worked for 3 people, he could not extend it to work for 4, so he proposed the problem to 2 of his Polish colleagues, Stefan Banach and Bronislaw Kastor. Stefan Banach was a mathematician who had attended school in Krakow, Poland. He worked at Steinhaus's Polish Mathematical Society, where he would be elected president of the society in 1939. Bronislaw Kastor was also a Polish mathematician, who upon graduating from the University of Warsaw would go to work with Banach under Steinhaus. In the mid-1940s, they solved this problem by producing the last diminisher procedure, allowing them to have fair division between 4 people. This method, like the lone divider procedure before it, proved to be proportional but not envy-free. While Steinhaus, Banach, and Kastor all contributed to fair division, the first constructive procedure for envy-free allocation actually wasn't until 1960. This procedure, however, wouldn't have been possible without the contributions from Banach, Kastor, and Steinhaus.
Okay, I'm going to be explaining how the math behind cake division works. So there are a couple of ways that you can do this, and the goal is that the cake division will be both proportional and envy-free. So one method of doing this is divide and choose, where you cut the cake into 2 pieces. Player 2 would choose the piece that they wanted, and player 1 would feel they were both equal because they were the ones that made the cut. This is both proportional and envy-free. Lone divider method is a 3-player version of this, where person 1 would cut the cake into what they felt were 3 equal pieces. However, this doesn't necessarily mean that it will be envy-free. So, I have a cake like this. I feel that's in 3 equal pieces. Player 2, or blue, wants this piece here. However, the 3rd player, who's in red, also wants this piece here. So that obviously creates a problem with envy. So what you could do in this situation is say, okay, I want the bottom half. I'm player 1, so that's fine. Neither of them want this bottom half. And then they take the remaining 2 pieces, kind of squish them back together and say, all right, we'll cut it about here. We feel that's even between these 2 pieces, and they're both then satisfied. However, that only works for really 3 people. So another way of doing this is the last diminisher method, and you can use with 4 plus amount of players. So for this example, player 1 would cut the cake into however many people are there, so we'll use 4 for this example. He then passes it to player 2. Player 2 would then maybe trim a piece, or they could say, no, I'm satisfied, and pass it to player 3. And they would do so on and so forth until they were done with all the players. So this would even out to being proportional, but not necessarily envy-free, because I, as player one, said in the beginning that all 4 pieces were proportional, but by the time that everybody else down the line has trimmed and cut and taken away different pieces, I may no longer feel that it is proportional. So to solve this problem, mathematicians Selfridge and Conaway came up with a new method. However, this also really only works for 3 people, and it goes in 2 parts. So the first part has 5 steps. So I, again, as player one, would cut a piece of cake into what I thought were 3 equal pieces. Player 2 could then look at the cake and say, I either think that all 3 of these are equal, or they could say, I'm going to trim a little bit there. So then they would pass it to player 3, and player 3 would choose whichever piece out of the 3 that they wanted, excluding this little trimmed bit. Then it would go back to player 2, and if player 2, if the trimmed piece had not already been picked, then player 2 would then choose that piece, and player 1 would get whatever is left. This part is envy-free because player 1 felt they were all equal to begin with. Player 2 got to make a two-way tie between the 2 largest pieces. So whichever piece they got, they feel is equal of at least 1/3. And player 3 chose first, so they would obviously be satisfied with their choice. The second part of this would be taking this little sliver here, so we'll move it to there, and dividing that evenly among the 3 of them. So this part would start with player 2, and they would say trim it or cut it into 3 equal pieces. Player 3 would then look at the pieces and say, oh, I like this, oh, I don't like this, I'm gonna trim a little bit or not trim a little bit. It would then go to player 1, and they would choose which piece they wanted. Player 3 would then do what player 2 did in the first half, and player 2 would get whatever is left. This is also envy-free because player 1 thought they were all equal to begin with. Player 3 got to make the cut and trim and adjust to which piece they wanted, and player 2 cut these 3 pieces out individually, so they already began with thinking that they were even. Again, like I said, this only works for 3 people. There are other ways to do it. Another method is fair division, but that was not covered in our chapters, so that's all I will be discussing today.
So the question is, why is cake division important? Well, it has everything to do with fairness, which by definition is the quality of making judgments that are free from discrimination. As stated earlier, the cake division procedure for a number of players is a procedure that the players can use to allocate a cake among themselves so that each player has a strategy that will guarantee that a player a piece with he or she is, quote, satisfied, even in the face of collusion by the others. Now, the cake division problem has stumped a lot of brainy mathematicians in the world for many years. There have been over 50 years of research done on cake cutting. Yeah, cake cutting. That's half a century to cut a cake. That's ridiculous. The subject is cake, but mathematicians say that you can use the cake division process for other problems in real life, such as my personal favorite, divorce settlements, which is an arrangement, adjustment, or other understanding reached as in a financial or business proceeding between 2 adults who have chosen to divorce. Ain't that right, Kara? Yeah, I'm getting a majority of this stuff. Just saying, because I know the cake division procedure. Other real life situations you can use this procedure is with electronic spectrum, frequency allocation, airport traffic management, you know, the guy with the big cones going like this, doing that stuff. Yep, that's cake division. Also, the exploitation of Earth's observational satellites. That's a mouthful right there. The application of cake division includes dispute resolution as fair division.
Hello, Math 111. I'm McKenna, and we will be discussing 13.6 and 13.7 sections. Oh, God.